Myself, Dr. Somir De, teacher in charge and assistant professor of mathematics section under Department of Basic Science and Humanities, Asansol Engineering College. So this is lecture number 6 under module number 4. Topic is range of T, kernel of T of a linear transformation. Under module name vector space. Paper name is Mathematics 1A, paper code BSM-101. And this subject belongs to BTech first semester computer science and IT, that is information technology. In my last lecture, that is in lecture number 6, I had discussed definition of linear transformation and how to prove one transformation is given, whether it is a linear or not. And in the linear transformation checking, there are two formula. One is combined, one is separate formula. I had discussed with both process with numeric examples, and lastly I had discussed one problem by which we can find the linear transformation. Okay, some informations were given and by which we can calculate the corresponding linear transformation. This is an extension of this lecture. In lecture number 6, I will solve some, or I will discuss some problem based on linear transformation, and then I will discuss definition of kernel of linear transformation, or kernel of transformation, as well as range of transformation or linear transformation and related problems. Okay. So let question number 3, let R colon R cube to R cube be a linear transformation such that T100 is equals to 1, 2, 3, T0 linear transformation on 0, 1, 0 is equals to 1, T1, 1, 1, and T0, 1 is equals to 3, 4, 5. Then determine the T. Same process like last video, last lecture. Let zeta is equals to xyz be any arbitrary vector in R3, that is domain. So this zeta xyz can be expressed with the help of 1, 0, 0, 0, 1, 0, 0, 0, 1. Suppose you have a question in your mind, sir, can I get each and every time 1, 0, 0, 0, 1, 0, 0, 0, 1? Not necessary. So I will give some example, no problem. This zeta, that is xyz, can be expressed x 1, 1, 0, 0 plus y 0, 0, 0, 1, 0 and z 0, 0, 1. Okay, since T is a linear mapping, so therefore T zeta is equals to x of T 1, 0, 0 plus y of T 0, 0, 0, 1, 0 plus z T of 0, 0, 1. So from the given information, T1, 0, 0 is equals to 1, 2, 3. So that's why x 1, 2, 3 plus y 1, 1, 1, because T of 0, 1, 0 is equals to 1, 1, 1. Similarly, T of 0, 0, 1 is equals to 3, 4, 5. If I simplify this component, if I add component wise, what we get, that is x, y plus z, 3z, comma 2x plus y plus 4z and 3x plus y plus 5z. So from it is clear that is T x y z, that is T zeta is nothing but T of zeta is equals to T of x y z. T of x y z is equals to x plus y plus 3z, comma 2x plus y plus 4z, comma 2x plus y. Sorry, you have I have mistake. It should be plus 5z. So that is equation number 1. Therefore, 1 gives the required linear transformation of T. Okay. Next. Now this is your question. Suppose in last question, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. You have a question, can I get each and every time 1, 0, 0, 0, 1, 0, 0? No, not necessary. Now try to understand in this problem, we have different types of form. Then try to understand how to solve it. Let T colon R cube to R cube be a linear transformation such that T 1, 0, 0, 1, 3, 2, T 1, 1, 0 is equals to 3, 4, 0 and T 1, 1, 1 is equals to 2, 2, 3. Okay, so first find that linear transformation and then find T of 1 to 1. Let's see. Let zeta is equals to x, y, z be any arbitrary vector in R cube. So let zeta is equals to a1, 100 plus, try to understand, A2 110, A3 111. Try to understand the basic difference. So if you have a 100010001, so you can express your XYZ in terms of this. But here what we are doing this A1 100, what we have, there is no relation with the XYZ. So here we have to calculate the value of A1, A2 and A3. Clear? Try to understand, very simple. So if you have a different form, so you have to write A1, whatever the form you have. Suppose in this problem 100 A2 into 110 plus A3 11. Clear? Please memorize. Please remember, if you have 100,010, that directly basis if you have, then you can associate XYZ directly. But if your information is not like 100,010,001, then you have to proceed like this. Okay, where A1, A2, A3 are three real number to be determined. So now what is zeta? Zeta is nothing but the XYZ. So from here, if I add all together, what is left? That is A1 plus A2 plus A3 comma A2 plus A3 comma A3. Clear or not? That is first component you have, second component A1 is missing, third component A1 is missing. So that's why you have A1 plus A2 plus A3. That is first component A1 plus A2 plus A3. Second component 0 plus A2 plus A3. Third component 0 plus 0 plus A3. Clear? So if I compare the component wise, A1 plus A2 plus A3 is equals to X, A2 plus A3 is equals to Y, A3 is equals to Z. Clear? So from here it is clear that what is our target? Our target to find the value of A1, A2, A3. Clear? So from it is clear A3 is equals to Z. If I substitute the value in this case, so A2 is equals to Y minus Z. When I put A2 and A3 in equation number 1, this equation, so we can get the value of A1. A1 is equals to X minus A2 minus A3. What is A1? A2 is equals to Y minus Z. What is A3? It is Z. So ultimately what we have simplified after simplification, X minus Y. So from here it is clear your A1 is equals to X minus Y, A2 is equals to Y minus Z, and A3 is equals to Z. Okay, so from it is clear, you may write zeta is equals to xy 100 plus y minus z 110 and z 111. Clear? So this is the basic difference compared to other last question. Okay, now since t is a linear transformation, so you may write t zeta is equals to x minus y t of 100 plus y minus z t of 110 z t of 110, because since t is a linear transformation. So from the given information, that is t 100 is equals to 123. Okay, so substitute here 1 2 3 t 100 is equals to 123. Similarly t 110 is equals to 340. So you should write 340, and t 111 is equals to 223. So you should substitute here 223. Now just to check component wise. Okay, first component, second component, third component, that is first component x plus x minus y, first component y 3y minus 3z, first component 2z. If I add all together, so this is the first component. Clear? I repeat once again, x minus y into 1, x minus y. First component 3 into y minus z, that is 3y minus 3z, and first component 2z. Similarly 3x minus 3y from second component, 4y minus 4z second component, and from here 2z, and here 2x minus 2y first third component, and then 0 into something means 0, and plus 3z. What is left after simplification? What you have from this, x plus 2y minus z, from second component 3x plus y minus 2z, and from third component 2x minus 2y plus z. So therefore your txy is equals to, you have this. So this relation 1 is the required linear transformation T. Okay. So what is the next part? You want to find T1 to 1. Now you know T x y z. Now substitute x equals to 1, y is equals to 2, and z equals to 1. Now substitute here 1 plus 2 into 4, 2 into 2 minus 1, comma 3 into 1 plus 2 minus 2 into 1. 2 into 1 minus 2 into 2 plus 3 into 1. After simplification, what you have? 1 plus 4 minus 1, 3 plus 2 minus 2, 2 minus 4 plus 3. So ultimately you have 4, 3, 1. So this type of question you can expect in your question paper. Now properties of linear transformation. Let T colon V be a linear transformation, then the linear transformation T has the following properties. T theta is equal to theta dash, where theta is the theta and theta are the null vector of V and W respectively. T minus alpha is equals to alpha vector is equals to minus T alpha for all alpha belongs to V. Cut T is a, I will discuss the definition of cut T. Cut T is a subspace of V and range T is a subspace of W. The mapping T is 1-to-1 or injective if and only if cut T is a singleton vector with phi, that is null. If alpha 1, alpha 2, alpha 2 be a linearly independent set of vector in V, then T alpha 2, alpha 3 dot alpha R is linearly independent set of vectors in W. If alpha 1, alpha 2, alpha dot alpha n is a basis of V, then T alpha 1, T alpha 2, T alpha n will be a basis of range T. Okay. If alpha 1, alpha 2, alpha n generates V, then T alpha 1, then T alpha 2, the T alpha n generates the range of T. These are very informative information. I'll show you some example. T plus T1, T2 alpha is equals to T1 alpha plus T2 alpha, where T1 colon V2 VW and T2 colon V2W are two linear transformation. But if you have a in general n number of linear transformation, then T1 plus T2 plus T dot Tn alpha is equal to T1 alpha plus T2 alpha plus T2 alpha plus dot Tn alpha, where T1 V2W, T2 V2W, and Tn V2W are n linear transformation. Now, a range of linear transformations. Try to understand. So this is also very important in part. Let T colon V to W is a linear transformation, then TV is a subset of W, then the set TW is known as the range of the linear transformation T, and it is denoted by range of T, range T or RT. Clear? Range of T or RT is equals to beta belongs to W, where T alpha is equals to beta, where alpha belongs to V. I repeat once again. Let T colon V to W is a linear transformation, then TV is a subset of W. This set TV is known as the range of the linear transformation T, and it is denoted by range of T or RT. This range of T or RT is defined as beta belongs to W such that T alpha is equals to beta. So you have to identify those beta what you have from T alpha, where alpha belongs to V. So I'll give some question, then automatically you can understand. Kernel of a linear transformation. Let T colon V to W be a linear transformation, then the kernel of T is generally denoted by cut T or NT, and it is defined by cut T or NT. Alpha belongs to V such that T alpha is equal to theta dash, where theta dash is the null vector of the codomain set of T, codomain of T, that is W. Sometimes the range of T is denoted by image of T or image T called cut T by null space. Okay. Try to understand with some example first. Now, rank of and nullity of linear transformation. Let T colon V and W be a linear transformation. Now, the rank of T is defined by the dimension rank of T is defined by the dimension of range T. That is the number of linearly independent vectors in range T. Clear? This type of question you can see, one information is given, find rank of T, nullity of T. Okay. Similarly, the nullity of T is defined the dimension of card T. That is the number of linearly independent vectors in card T. I repeat once again. Rank and nullity of a linear transformation, let T colon V to W be a linear transformation. Now the rank of T is defined by the dimension of range T. That is the number of linearly independent vectors in range T. So this number is called rank of T, and the nullity of T is defined the dimension of card T, that is the number of linearly independent vectors in card T. Now try to understand, very simple. Let a mapping T colon R cube to R cube be defined as T xyz is equals to x plus 2y plus 4z, comma 2x plus y plus 2z and minus x plus y plus 2z. Then show that T is a linear mapping, and also find card T and dimension of card T, range T and rank T. Okay, try to understand, very simple. So already you know how to prove it's a linear. I should repeat once again. Let alpha and beta be two vectors in R cube, that is such that alpha x1 y1 z1 and beta x2 y2 z2. So T alpha is equal to T x1 y1 z1. So already I discussed how to find the value. So T alpha T x1 y1 z1 is equals to, from here, x1 plus 2y1 plus 4z1 comma 2yx1 plus y1 plus 2z1 minus x1 plus y1 plus 2z1, and T beta is equals to 2x2 comma y2 comma z2 is equals to x2 plus 2y2 plus 4z2 comma 2x2 plus y2 plus 2z2 comma minus x2 plus y2 plus 2z2. This result is also coming from here, the given relation. Okay, now we want to prove there is a linear transformation. So that means you have to prove T alpha plus B, T A alpha plus T beta is equals to A T alpha plus A T beta. Let's see. Now T A alpha plus T beta B beta is equals to A T A x1 plus B x2, because A alpha plus B beta. Okay, so A y1 plus B y2 comma A z1 plus B z2. Clear? Very simple. Please check. Please check. That is A x1 y1 z1 plus B x2 y2 z2. So automatically you may write A x1 plus B x2 comma A y1 plus B y2 comma A z1 plus B z2. So this is the logic behind this. Okay, so that's why you have this. Okay, so now you substitute these three components in this relation, that is A x1 plus B x2 plus 2 A y1 plus B y2 plus 4 into A z1 plus B z2 comma 2 of A x1 plus B x2 plus A y1 plus B y2 plus 2 A z1 plus B z2 comma, it should be comma, this comma is missing. Okay, that is, it should be comma. Okay, that is minus A x1, minus of A x1 plus B x2 plus A y1 plus B y2 plus 2 of A z1 plus B z2. So that means I have substituted these all three components into this relation. So that's why I have this. Now So if I take common A, x1 plus 2y1 plus 4z1 plus B, x2 2y2 plus 4z2 comma, okay, A 2x1 plus B plus y1 plus 2z1 plus B 2x2 plus y2 plus 2z2 comma A minus x1 plus y1 plus 2z1 plus B minus x2 plus y2 plus 2z2. So what we are doing basically very simple. We extracting you. I'm taking A common from first part A common and B common, second part A common and B common, from third part A common and B common. Now you take common A from first part, that is x1 plus 2y1 plus 4z1 comma 2x1 plus y1 plus 2z1 comma minus x1 plus y1 plus 2z1. So that means A is common from first part, this one and that one. Similarly, plus B, x2 plus 2y2 plus 4z2 comma 2x2 plus y2 plus 2z2 comma minus x2 plus y2 plus 2z. Okay, so this first component is nothing but T alpha, that is A T alpha, plus this portion is nothing but T beta, T beta. So from here it is clear that is your T A alpha plus B beta is equals to A T alpha plus B T beta. Therefore, the mapping T is linear. So our first part is over. Now we want to find the cart T and dimension of cart T, range T and rank of T. Let's see. Now find cart T. Let delta is equals to x3, y3, z3 belongs to cart 3. Any. So all you know for cart T, T delta is equals to theta. This theta is nothing but null vector, belongs to R cube. So T x cube, x3, y3, z3 is equals to this T delta is equals to how much? x3, y3 substitute here. So this T x3, y3, z3 must be satisfy the given relation. This relation must be satisfied. So that means x3 plus 2x 2y3 plus 4z3 comma 2x3 plus y3 plus 2z3 comma minus x3 plus y3 plus 2z3 is equals to, on the right side what you have, theta, that is 0 0 0. So you have three components. So if comparing this component wise, you may write x3 plus 2x3 plus 4x3 plus 2y3 plus 4z3 equal to 0. 2x3 plus y3 plus 2z3 equal to 0 minus x3 plus y3 plus 2z3 equal to 0. So what is our target? Our target to find the value of x2, x3, y3 and z3. Now using by using cross multiplication technique, we are considering both first and 2. So x3 by 0, y3 by minus 2 minus 4 and z3 is equals to 3 by kc. So from it is clear that y3 is equals to minus 2k and z3 is equals to k. Suppose you have a doubt in human why I'm taking this, because this 3 is common from both. So that's why I'm taking this. Otherwise, you may consider only k. After that, you have to separate this. So delta is equals to x3, y3, z3 is equals to k 0 minus 2 1. So therefore, cut t is equals to span of. So a different values for what is delta? Delta is the arbitrary vector of cut t. Correct. So from here it is clear that each and every vector of cut t can be expand with the help of this vector for different values of k. So therefore, cut t is equals to span of 0 minus 2 1. Okay, so how many vectors you have? So only one vector you have. So therefore, the dimension of cut t is 1. Clear? Now, so this is all about the calculation technique for cut t. Now try to understand Next, to find the range of T, let eta be a vector in Rt, any vector. So that means your eta is equals to x3, x4, y4, z4. Okay. So zeta you can write, eta you can write x to the a. This also satisfies this relation, this one. Okay. Zeta x4, y4, z4 satisfied 4x4 plus 2y4 plus 4z4, comma 2x4 plus y4 plus 2z4, comma minus x4 plus y4 plus 2z4 for some x4, y4, z2 belongs to Rq. Now try to understand very simple. What is the coefficient of x4 from here? Just to check. Zeta is equals to x4. What is the coefficient? 1. What is the coefficient? 2. What is the coefficient? -1 right here. So x4, that is 1, 2, -1. What is the coefficient of y4? 2. What is the coefficient of y4? 1. What is the coefficient of y4? 1. That is 2, 1, 1. And then what is the coefficient of z4? 4. What is the z4? 2. What is z4? 2. So from it is clear z4. So from it is clear this zeta, that is where x4, y4 are arbitrary, so can be expressed with the help of these three vectors, that is 1, 2, 1, 2, 1, 1 and 4, 2, 2. So from here it is clear that these 2, 1, 1 and 4, 1, 1 basically are linearly dependent because both are same. If I take common 2, so you can consider anyone. So that means this Rt can be expressed, that Rt can be expand, that is range of T can be expand with the help of these two vector only, 1, 2, -1 and 2, 1, 1. Okay. So how many vector linearly independent, because these are linearly independent, you can check. So how many linearly independent vector you have? 2. So that's why the rank of T is 2. Okay. So this is the example by which you can check how to calculate card T, how to find the range of T and dimension of card T and dimension of range T. Now another example, same type problem. If a linear transformation T colon R cube to R cube defined by T xyz is equals to x plus 2y plus 3z, comma 3x plus 2y plus 5z and x plus y plus 2z, then find x, y, z belongs to R, then find rank of T and nullity of T. Okay. So here, same ways you have to find the card T and range of T, then find it. So here no need to, here linear transformation is given. So here linear transformation T colon R cube to R cube is defined by T x y z is equals to x plus 2y plus 3z, comma 3x plus 2y plus 5z, comma x plus y plus z, where x, y, z belongs to R. Let alpha, beta, gamma belongs to one vector belongs to, I forgot to mention the bracket. So alpha, beta, gamma belongs to card T. Then T alpha, for definition of, from the definition of card T, T alpha, beta, gamma is equals to 0, 0, that is null vector. Okay. So from it is clear, if we substitute here, that is alpha plus 2 beta plus 3 gamma, comma 3 alpha plus 2 beta plus 5 gamma, comma alpha plus beta plus 2 gamma is equals to 0, 0, 0. If I compare component wise, alpha plus 2 beta plus 3 gamma and 3 alpha plus 2 beta plus 5 gamma equal to 0 and alpha plus beta plus 2 gamma is equals to 0. Okay. Okay, so from it is clear that clearly the coefficient of determinant system is vanishes. So the coefficient of determinant of the system vanishes, and so Kamasul, the system of equation has infinite number of solution. If I subtract 1 minus 2, what we get? So one relation in terms of beta and gamma. So that means, so if I take the solution alpha is equals to C, So automatically beta is equals to C and gamma is equals to minus C. Okay. Now cut T is equals to alpha beta gamma, that is span of alpha beta gamma, that is C minus 1 minus C. That is, if I take common C, that is C is a arbitrary real number, so 1 1 1. So that means every vector of cut T can be expressed in terms of 1 1 1 vector. So therefore the nullity of cut T is 1, since the cut T is generated by only one vector. Now the rank nullity theorem, rank of T dimension of R3 by nullity of T. What is nullity dimension of R3 is equals to 3, because so this is a three-dimensional operation. So that means your T is defined R3 to R3, three dimension. So that the dimension of R3 by nullity of T is equals to the rank of T is equals to 2. Okay. So this is the another example by which you can calculate dimension nullity of T as well as rank of T. So try to solve some question based on this concept. Okay, thank you.